Well, this will be the last lecture on mirror machine. In this we will discuss a simple mirror configuration, then we will review electron ion confinement and find a scheme of plasma heating, and the important scheme is adiabatic compression. Then we shall discuss or deduce rather an important equation that J cross B should be equal to gradient of pressure for plasma confinement, and to achieve minimum B configuration, what kind of arrangements we make, we use rather I of A bars, and there are two important instabilities in cylindrical plasma systems. One is interchange mode and the other is kink instability. So we shall discuss a little bit of these instabilities, and as I was mentioning, drift cyclotron loss cone mode instability is also serious concern in a mirror machine. We shall discuss that, and then we will discuss some applications. Two prime applications are always to be kept in view. One is the application in a fusion device. Mirror is a fusion machine. Actually, it has a tremendous attraction at one time. The interest has declined significantly over the years in comparison to a new device called tokamak, but still there is a lot of interest in this machine. Another important application of a mirror machine is in producing plasmas of very high density for plasma processing of materials. And third one, there is a natural mirror near the pole, in the polar region of ionosphere, and where the charged particles coming from the sun emitted from there as solar bursts, they precipitate near the polar regions, near the poles, where the magnetic fields lines of force concentrate, and in that case the precipitation gives rise to concentration of those particles, and they give rise to a very special kind of radiations in the auroral region of ionosphere. So those are some interesting phenomena. We shall, if time permits, we shall discuss them. Now let me begin with a simple schematic of a mirror. Well, mirror essentially is a tube, long tube, several meter long, and it has a connection to a vacuum system, vacuum pump, and these pumps create an evacuation. Initially you evacuate the system to a pressure of typically 10 to the power minus 6 torr, and one must remember 1 torr of pressure is equal to 1 millimeter of mercury. HdG is the pressure, where d is the density, h is the height of the mercury column, and g is the acceleration due to gravity. So 1 millimeter of mercury means h is 1 millimeter, d is 13.6 gram per centimeter cube, and g is around 980 centimeter per second square. So from there you can deduce in dynes per centimeter square the pressure. So L at this pressure, if you calculate the number of atoms, it is quite small. Then you fill in a desired gas here. For fusion you would like to fill in this with deuterium tritium plasma, but for other experiments you can use other gases like nitrogen, helium, etc. And I would just like to mention that typical pressures that which you fill in the gas in these machines. So gas pressure is in the range 10 to minus 3 to 10 to minus 4 torr. At 10 to minus 4 torr, the atom density turns out to be typically of the order of 3 into 10 to the power 12 per centimeter cube. So, the mirror machine plasma, if it is fully ionized, would have electron density around 10 to 12, 10 to 13 electrons per centimeter cube. So, this is the vacuum system, and then there are field coils here that will produce a mirror magnetic field. And typically magnetic fields around a kilogauss, a few kilogauss is created in the central region, this region, and plasma is contained in this region. The lines of force, as I have demonstrated earlier, go like this. And plasma is confined in this region. So, plasma is, I can show something like here. However, it has been, and we shall learn today, that mirror reflection alone is not sufficient for plasma confinement. Mirror reflection simply tells that the electrons which have an angle, pitch angle greater than critical the loss cone angle theta c, these ions and electrons will be confined, But there can be instabilities that will not help, that will not let this equilibrium persist for long. But people found that a suitable configuration for plasma confinement is the one for which there is a minimum in a magnetic field. So, the magnetic field should be minimum when you move in the z direction or along the axis of the machine, and it should be minimum when you move in the transverse direction. To achieve that, people employ 4 bars called I of A bars. One is here, carries current in one direction, another is here that carries current in the other direction, called I of A bars. And there are 2 coils, one on top, one below. So, there are 4 current carrying wires that will produce a magnetic field that will superimpose with the magnetic field produced by these coils. These are the axial field coils, and they will produce magnetic field like this. These will produce magnetic field like this, and one can achieve a minimum B configuration for plasma confinement. Well, as far as the heating is concerned, what really happens that in order to increase the temperature of the system, you need to supply energy from outside. Initial heating is achieved by what we call as adiabatic compression. Initially you apply, well, first of all you create a plasma here by RF discharge when these fields are very small, and then suddenly you increase the magnetic field. When magnetic field increases, we shall learn in a little while, then mu still is a constant of motion, means the magnetic flux linked with every orbiting electron is a constant of motion. So, when B field increases, V perp must also increase, and in this case energy is not a constant of motion, mu is a constant of motion. So, when B field increases in time, then any time varying magnetic field will produce an electric field, and that will give energy to the particle, and its kinetic energy increases, and from the electric field that is produced by the time varying magnetic field. So, plasma is heated. So, we shall learn about adiabatic heating. Let me look into this problem of adiabatic heating. Let me look into the energy gain. Rate of change of energy d dt, for instance, of half m v per pi square is the kinetic energy of the electron. So, I want to find out how this is. I am considering an electron which is gyrating in a magnetic field, say Bz, around the axis, and when the B field increases in time, its magnitude increases in time, I would like to find out how much the energy of the electron increases. Then the B field will time varying B field will produce an electric field. Suppose the value of the electric field is E into, this is the force on the electron which is gyrating. So, if the electric field, if the electron is gyrating in the phi direction, if there is an electric field in the phi direction, then there will be work done by this. Per second would be product of these two, the electric force multiplied by the displacement per second is called the work done by this electric force on the electron, and hence should equal the energy increase, rate of increase in energy of the electron. So, if I want to find out the work done in one cyclotron revolution, so work done or change in energy rather, change in energy in one cyclotron period. I am considering that the magnetic field is changing very gradually. So, let me calculate the change in energy of the particle in one cyclotron period. How much that would be? I must multiply this by dt and integrate minus E dot V, I can write down dl by dt. If the electron length is this, dl by dt is for V into dt, and let me integrate this from time 0 to 2 pi upon omega c. Let me calculate this quantity, and the electric field satisfy this equation, curl of E is equal to minus delta B by delta T from the Faraday's law of electromagnetic induction. So, what I am going to do, dt will cancel out. This is a line integral which by using Stokes theorem I can write down in terms of curl of E, and let us see what do I get. So, change in energy in one cyclotron period is half m v per pi square is equal to minus E, this becomes curl of E dot ds, the area, and curl of E will be delta B by delta T. So, this becomes is equal to E delta B by delta T into ds. Now, this quantity, let me just a second, let me this quantity delta B by delta T is fairly constant over the orbit of the electron, over the cross section over which the electron is rotating. So, I can approximately write this as E delta B by delta T, and ds is pi Larmor radius square V per pi square upon omega c square. And this quantity on the left hand side is change in, if I write down this in terms of mu, then this is mu into B. So, mu B is equal to this quantity and this is in this is the quantity I must evaluate, change in this quantity in one cyclotron period. In one period. So, what really happens is this is the quantity which is equal to mu into delta B in one cyclotron period, delta B by delta T in one cycle, change in this quantity in one cyclotron period and multiplied by one cyclotron period. So, this becomes the change in B in one cyclotron period, and this gives you mu as a constant of motion. This is a very important observation, that earlier we had derived mu as a constant of motion for a time independent magnetic field which was inhomogeneous. Bz was a function of z, and we found that as the electron goes from the middle of the mirror towards the throat, then mu remains constant. But here we have found that an electron gyrating about the line of force, even in the center of the machine, it may not have any z direction, z velocity, but it will gain energy from the electric field because magnetic field is changing with time, and magnetic field when changes with time, then if the magnetic field changes by delta B, energy will increase by this amount. So, mu really remains a constant, because this you can write down as mu delta B plus B delta mu. And what does it tell? That if mu is a constant of motion, adiabatic invariant, this is equal to m v perp square upon 2b. So, whenever b increases with time, v perp must also increase, so energy increases. So, if you can increase the magnetic field by a factor of say 10, you are increasing the particle temperature by a factor of 10, because this is like temperature of the electron or ion, depending on what particle you are considering. So, that is an important result. So, adiabatic compression means whenever you increase suddenly the electric magnetic field in the field coils, then the plasma which is already there will acquire higher and higher temperature, and this way you can achieve temperatures to the tune of maybe 100 electron volt. The issue is how will you increase the temperature beyond that point. Beyond that point you require radio frequency waves, or you require neutral particles, neutral beams. And both have been employed in mirror machines. There have been lot of experiments in heating by using waves, electromagnetic waves of frequencies around ion cyclotron frequency or electron cyclotron frequency. So, of the wave frequency omega around omega Ci and omega of the order of omega C. This is the ion cyclotron frequency and this is the electron cyclotron frequency. These waves can preferentially heat ions or electrons depending on whether the frequency is close to ion cyclotron frequency or electron cyclotron frequency. And neutral beams can be launched into the machine, and by charge exchange collisions they get ionized over there in the system, and they can deposit their energy on the plasma ions and heat the ions. So, temperatures of the order of kilo electron volts can be achieved by these techniques. Well, the two issues are important in here, that is the system macroscopically stable, and I would like to bring out two important instabilities rather qualitatively today. One is very similar to Rayleigh-Taylor instability, and this is called interchange mode. Instability. Please keep in view that we are always talking about a axially symmetric mirror, for instance. And if I have a plasma here, I am expecting the plasma to have some sort of azimuthal symmetry. So the plasma has a symmetry. If I cut any cross section here, suppose I look at this cross section here, the plasma here will look circular. So let me make a circle here. This is the circular cross section, so I can consider my plasma bar of uniform density. I am saying that the plasma is filled inside this and there is no plasma outside. And your magnetic field is perpendicular to the plane of the board going upwards. So now this is the direction of magnetic field. Now please note here, the mirror machine has curvature, the lines of force have curvature. Here the curvature is in the radial direction, outward, whereas near the throat the curvature is in this direction, inward. So what are you expecting here? This is a situation where after all plasma is of high density placed here. Density increases when one goes towards the center of the plasma, and here you have curvature opposite to the density gradient, whereas in this region where the curvature is towards the plasma and density gradient is also towards the plasma, so they are in the same direction, and in a little while we shall learn that this region is called a good curvature region and this is called a bad curvature region because there is a possibility of growth of a perturbation. Let us see how it happens. We have learned earlier that if there is a system in which there is a magnetic field Bs, and if there is a force exerted on a particle electron, for instance Fe, then this electron will move with a drift velocity V0, which is equal to Fe cross Bs upon charge of the electron minus E into Bs square. Similarly, if ion experiences a force Fi, then V0 of the ions would be F of the ion cross Bs, magnetic field, static magnetic field, upon E Bs square with a positive sign. The interesting part here is that the curvature drift, for instance, after there is a curvature in this magnetic field, so curvature drift has Fe for electrons. This force is equal to mass of the electron into parallel velocity of the electron along the line of force square upon this divided by the radius of curvature, and this is in the direction of radius of curvature. A similar expression I can write down for Fi, and this is equal to mass of the ion V parallel of the ion square upon radius of curvature and Rc cap. You may note here that the electrons, if Rc is in the direction like this, in the radial direction, and this magnetic field in the z direction, then R cross z would be in the phi direction, minus phi. So this becomes parallel to phi. The value would be m V parallel square upon E B S into R C, and that will be in the phi direction. And for the ions this would be, if I put this expression, this is radial direction, this is the z direction, so r cross z is minus. So minus m I V parallel I square upon E B S R C into phi cap. Means the electrons and ions in the plasma here, they are, besides going gyration about the lines of force, will try to move. This is, please note here, the electrons and ions are gyrating about the lines of force like this, but then they will be having a phi motion. So they will be going, electrons will be going in one direction, the ions will be going in the opposite direction, like this. So if I plot this, the cross sectional, in the cross sectional plane, this is my x axis, this is my y axis. I measure phi, suppose electrons are travelling here, this angle is phi, phi direction is here. So electrons are going this way and ions are going this way. This is electrons go this way and ions travel in the opposite direction. I think I can draw ions like this. So in the plasma, because of curvature, the electrons and ions will go round in these directions, in opposite directions, and this is just because of the curvature. You can add grad B drift also, that reinforces with this, the directions are same. So for the electrons, the curvature drift and grad B drift are in the same direction phi, and for ions also curvature and grad B drifts are in minus phi directions. Now what is going to happen? If I perturb this isobaric surface, the surface over which the plasma pressure is uniform, if I perturb this, suppose the plasma is slightly displaced, interchanges position. Let us see what I mean. I am considering that, suppose this is the cross section of the plasma, and let me consider, well, let me divide this. Let me just see what kind of picture I want to draw. Yeah, let me draw a point here, a point here, a point here, a point here. So let me draw a picture like this. This goes like this and then comes back like this, and let me take this like this. Suppose, well, this should be symmetric. I have not been careful in this. Means if I displace, suppose there is some displacement, some perturbation in the plasma, plasma moves from here to here, and the plasma from here moves there. What I am saying is that the electrons are rotating in this direction, so they will create a space charge, negative space charge here, and a ion positive charge will appear here. As a consequence, there will be an electric field in this direction. In this region there will be electric field in this direction, electric field in this direction in the plasma, and E cross B drift of electrons and ions will be in the outward direction. Similarly here, the electrons will charge will appear here, ion charge will appear here, there will be electric field in this direction, and E cross B drift will be in this direction. Thus, these portions will bulge more and more. So if there is a small bulging somewhere, then this bulging will grow, this ripple will grow, and the system will be unstable. So, the plasma will not be confined for a long time. This instability is very similar to relative instability that we discussed one day. In relative instability, but what happens is this. Let me recall a little bit. In a relativistic mode, we considered a plasma supported against vacuum or against gravity rather in vacuum. Gravity was downwards, and this had a magnetic field perpendicular to the plane of the paper. So, if I consider this to be my x direction, this was my y direction, and B field was perpendicular to the plane of this board in the z direction. No, x cross y will be into the board. So, this will dot here, this is into the board. Now, what happens that because of this gravity being perpendicular to magnetic field, the plasma which is filled in here, it acquires drifts, and the electron drift is in this direction and ion drift is in this direction. So, this is the electrons go in this direction and ions go here. And let us examine what is the consequence here. In the case of relative instability, if I have a small original surface and if I have a ripple here, then the electrons are going in this direction and ions going in this direction. The drifts are simply Vg on the electrons is equal to mg, the force, cross Bs upon E Bs square, and Vgi is equal to Mig cross Bs upon E Bs square. The first one is with a negative sign because electron charge is negative. Now, please note here that mass of the ion is much bigger than the mass of the electron, and consequently Vge is very tiny. This is the direction of Vge. Nevertheless, it is the relative velocity of the two that is important. So, what will happen? Ions will go in this direction, electrons will go in this direction, and there is a static magnetic field perpendicular to the plane of the board, and gravity is here. This is a static magnetic field. So, what will happen? That this portion will acquire a positive charge because ions will move. So, this becomes a positive charge here, there will be negative charge there, and there will be electric field here, and this electric field will pull the plasma downward by E cross B drift. So, what was happening in the relative instability situation, same thing happens here. The only problem here is that the drifts due to curvature in magnetic field and inhomogeneity in magnetic field are roughly equal for electrons and ions, but they are opposite direction. In this case of relative instability, the growth rate was gamma was under root G upon ln. How about here? What kind of G we have here? In the case of interchange instability, you just write down equivalent to G, which is equal to centrifugal acceleration for ions. So, if I replace G by V parallel square upon R, radius of curvature RC, just do this and you will get the growth rate for the interchange mode is equal to V parallel, this I am talking of ion divided by ln into RC under root. Ln is the density scale length, which is typically the radius of the machine, which is like 10-15 centimeter or so, and Rc is the radius of curvature, which is quite huge, of the order of length of the machine or even bigger. So, this is a large quantity, Ln is a small quantity, and V parallel I is the typically thermal velocity of ions. So, growth rate scales with under root of temperature and inversely proportional to the square root of minor radius of the machine, which is of the order of, or Ln of that order, and radius of curvature of the lines of force. It is a serious matter. So, please note here, the instability grows only when the density gradient and gravity are opposite to each other, but if you reverse the direction, then there is no instability. That is why I was mentioning that in a mirror the lines of force are like these. So, there is a good curvature here, there is a bad curvature here, because here the radius of curvature is outside and density gradient is inward. So, there is a bad curvature, this is a good curvature, and the region of good curvature is little, the region of bad curvature is bigger, and consequently the system is unstable. But if you put those I of A bars, then you change this structure here and you can suppress this instability. Well, people tried different ways to suppress this instability. One possible way is by using radio frequency waves. There was an experiment conducted on a mirror called Phaedrus tandem mirror. It was conducted many years ago, I think in 1980s, and the plasma of the Phaedrus mirror was tandem mirror. They considered a plasma, very long mirror was there, and they put a RF coil here in the middle. The magnetic mirror coils were here, and so on. Plasma was in here. Well, what they found was the fields that they employed were of frequency close to ion cyclotron frequency within 10%, and those fields were found to be effective in suppressing the interchange mode instability. This is also known as flute instability, and the main experimentalist was, this group was Farron, Herskovich, and team at the University of Wisconsin, and this was published in Physical Letters 1983. Well, we developed an explanation, a theory for understanding these results, and we found that if you can couple the unstable mode to a high frequency mode, then the ponderomotive force of the high frequency mode can stabilize by nonlinear coupling, can stabilize this instability. So, there are some efforts in stabilizing the macro instabilities in a mirror machine. However, there is another instability that is we call as kink instability. Let me just mention what it is. This instability is important in a machine, maybe not really so important in a mirror machine, but in any device that contains an axial current. So, suppose I have a plasma cylinder and there exists a current in there. Suppose Jz current density is there in the system, there is a magnetic field also here B as in the z direction. Suppose this is system, the plasma, very long plasma column. And suppose this plasma somehow acquires a kink, rather than going like this, it becomes like this. Suppose this is acquires some sort of rippling character along the length. Then what happens that the current is now shifting its directions, J goes like this. Then this will produce a magnetic field. Obviously, any current which is axial will produce a polyidal magnetic field like this. So these lines of force will be like this. But the lines of force will be away from here and they will come closer to here, each other. So B field is bigger here, polyidal magnetic field is larger here than here, and magnetic pressure becomes more here than outside here, and that tries to increase this ripple, this bulging. This is kink instability. This is of some concern in some machines which carry axial currents. Tokamak has a current and one should vary a instability similar to this instability there. But I think mirror machine should not worry too much about this instability. A more dangerous instability in mirror machine is related to loss cone distribution function of ions. In my last lecture, I mentioned that a mirror machine has electron distribution function which is Maxwellian, which is, as I mentioned earlier, F E is equal to N0 m upon 2 pi T e to the power 3/2 exponential minus m v square by 2 T e, where v square is v perp square plus v parallel square or vz square. Ions, on the other hand, are non-Maxwellian, obeying what we call as the loss cone distribution function. Loss cone distribution. And if I plot this, well, let me write this. F ion is equal to N0 mass of the ion upon 2 pi Ti 3/2 multiplied by mi v perp square upon 2 T I exponential minus m I v square by 2 T I. This v square is sum of v perp square plus vz square. This is only v perp square. This extra term here tells you that particles with small v perp are not there in the system. They are lost. Well, actually you can put some power here, that depends on the mirror ratio. So this is a typical loss cone distribution function that I have shown, and graphically this goes like this. Plot v perp here, f here, and this is like this. So this is a loss cone here. These particles are lost. and this gives rise to an instability whose frequency is very close to ion cyclotron frequency and also in the vicinity of diamagnetic drift frequency, which is equal to k of the wave number, k is the wave number of the unstable wave, into V thermal of the ions, thermal velocity of ion square upon density scale length in the machine into ion cyclotron frequency. So, from this condition one can get the value of k. Frequency of the mode is very close to omega Ci, and wave number is such that when you put this of the order of equal to omega Ci, you will get the value of k also. So, this is a low wavelength mode. This is a wavelength perpendicular to k, to DC magnetic field, and this is a very serious instability. This can grow on the time scale of the order of a millisecond. Unless you take remedial measures to suppress this instability. One remedial measure is that you try to fill the lost cone. You fill in particles to cover this loss. Certainly that is one possibility, but then you are to pumping particles, additional particles again continuously in the system. Second possibility was, and which was very fascinating at one time, there was very significant effort at Oak Ridge and other places, and the new device came into existence and they called it as Elmo Bumpy Torus. In brief, EBT. What they wanted to do, that in a mirror machine you are losing particles from the throats. So, if you put these mirrors on a toroid like this, suppose I have a mirror here with one set of coils here, then I have a toroid, another toroid here, then I have another toroid here, and then just around this. So, what will happen? You will have a line of force like this. And close it on a toroid like this. So, if you have a large number of such mirror segments placed and joining over each other in a toroidal sense, then the ions which are lost here will be filling the lost cone of the other mirror, the lost which are here and so on, and consequently they will be confined there. And what was found that normally in a tokamak you require a toroidal current to confine the plasma. In this way found that if you launch microwaves at second harmonic frequency, cyclotron frequency, then they can form here very hot rings near the midplanes of the mirrors, and these rings provide the stability against many instabilities, and plasma is confined. So, this is a very interesting way to fill in the lost cone that you are allowing the electrons or ions lost from one machine to go into the other and from the other to come to this one. So, there is a filling of the lost cone, and hence DCLC mode can be stabilized here. That was a very interesting device. I think still some work may be going on this machine, Elmo Bumpy Torus. And electron cyclotron resonance heating at fundamental and second harmonic was found to be very useful, especially second harmonic, were found to be very useful in heating the plasma. Obviously, electron cyclotron heating will heat the electrons, and those electrons will then have to transfer their energy via collisions to ions. So, this is a very interesting way of avoiding the DCLC mode, the drift cyclotron lost cone mode. I think I skipped one important consideration in plasma confinement, and that is the consideration for some macroscopic consideration for plasma confinement, and that is essentially I want to deduce a general condition that J cross B should be equal to gradient of pressure. This B is the static B field and this is the plasma pressure. For any confinement, this condition must be satisfied. If the plasma is uniform, there is no problem, you do not require a magnetic field. But if the magnetic field, if the pressure is not uniform, you require a current in the system and B field in the system. Let us see how this can happen. What is the, first of all, let me deduce this and then discuss some implications of this. First of all, you know that if a plasma has any pressure gradient or electric field, it will give rise to drift velocities. So, in the quasi steady state or a steady state, I will call this quasi steady state, the drift velocity of particles should not depend on time. So, dt should be 0 for electrons as well as ions. So, what I require, m dV by dt, which is 0 for electrons. If there is an electric field in the system, then the electrons will experience this force, electric force. If they are drifting with velocity v and there is a magnetic field, then they will experience a magnetic force. And if there are collisions between electrons and ions, then they will lose momentum, m nu into v minus vi. This is the relative velocity of electrons and ions. This is the momentum transfer from electrons to ions. And if there is a gradient in pressure for electrons, then this is Ne, Ne, Te. This is the equation of motion for electrons. In the steady state, I put this equal to 0. Similarly, for ions, this 0 will be, charge will be plus E, so Ee, and this will be E times Vi cross magnetic field. Then the momentum that the electrons lose is gained by the ions, so put the plus sign here, m nu v minus Vi. This is the collisional momentum the ions gain from the electrons, and similarly a term 1 upon Ni gradient of Niti. This is the equation of motion for ions. For electrons is this. What you can do, I want to avoid this E, add the two equations, and what you can do, you can multiply the first equation by electron density and this by the ion density, and recognizing that in plasmas quasi neutrality often holds. So, Ne equal to Ni if I take and add these two equations, then this momentum terms cancel out, electric field terms cancel out, and these two terms after removing Ni and Ne from here, they add up to give you gradient pressure, and remaining terms give you current density cross B. So, if I define current density J is equal to minus Ne into E into V, this is the electron current density, and ion current density is plus Ni E Vi. So, just by adding these two equations and recognizing that Ne is equal to Ni, quasi neutrality condition, then you get this condition J cross B is equal to grad P. But I wanted to tell you that if I put J from the equation of rather Ampere's law or Maxwell's equation, which says that curl of H or curl of B rather is equal to mu 0 J in the steady state when there is no displacement current. This is the Maxwell's equation. So J if I put from here, then I get interesting equation which says that B cross curl of B upon mu 0 plus gradient of P is equal to 0, where P is the sum of electron pressure plus ion pressure. Well, I think a detailed discussion on this we will have later, but here it will suffice for today that this equation, if I consider a one dimensional situation, suppose I have a plasma cylinder and my magnetic field is in the z direction, but I want to confine the plasma, so plasma pressure has a variation with r, this is my radial direction. So suppose I want to allow P as a function of r and B as a function of r, but the direction of B is in the z direction. Just substitute this here. This equation quickly gives you delta delta r of B square upon twice mu 0 plus P is equal to 0. Means B square by twice mu 0 plus P is a constant of constant. In this particular one dimensional case, when I have taken the pressure and magnetic field to vary with r, and what we find that the region where plasma pressure is more, B field has to be smaller and vice versa. So what you require, if I want to confine a plasma in this region, then the B field outside should be more than in the inside. The minimum magnetic field in the plasma you can have is 0. So the outside field has to be more than this value given by this equation. So a certain minimum magnetic field is required, and but actually very important quantity in plasma jargon is that called beta of the plasma, which is kinetic pressure P upon magnetic pressure B square by twice mu 0, and this turns out to be less than 1, only then you can satisfy this condition. This is important in a mirror machine or in any device. That is why a minimum B configuration is mandatory. The plasma should have a minimum magnetic field where the pressure is large. And I think with these few considerations, I think we have had a lot of interesting discussion, and we shall return to this later. Thank you.